Building and launching a self-propelled machine allows us to observe complex physical forces in real time. We are going to isolate and harness these forces using a few basic materials from around the house. You need a sheet of cardboard, 4 bottle caps, 2 drinking straws, 2 wooden sticks, some tape, scissors, and a rubber balloon. Step 1 is establishing the structural base. Cut a clean rectangular piece out of the cardboard. This will serve as the vehicle's chassis. Next, attach the 2 straws across the width of the cardboard base using tape or glue. These straws must be perfectly parallel to one another. Even a slight angle will force the wheels out of alignment, causing the vehicle to veer off course. Precision here is necessary. An accurate build ensures the physical forces we generate later will push the car in a straight line, rather than causing it to stall or spin. Now we construct the wheel and axle system. Thread the 2 wooden sticks through the parallel straws. Then, puncture a small hole in the center of each bottle cap and firmly attach them to the ends of the sticks. This diagram shows a cross-section of our wheel and axle setup. Notice the tiny gaps between the moving axle and the stationary straw. If the wheel rubs against the cardboard chassis, it creates kinetic friction, a physical force that directly opposes the rotational movement we need. If an axle is crooked or a wheel is mounted off-center, it creates unbalanced torque. Instead of rolling forward, the mismatched forces will drag on one side, sending the vehicle into a circular path. To prevent this, perform a manual spin check. Give each wheel a flick with your finger. They should rotate smoothly and independently, without catching on the cardboard base. Eliminating this mechanical resistance is the first requirement. A vehicle cannot propel itself forward until it is capable of rolling freely. With the chassis rolling smoothly, we can construct the power source. We will build a pneumatic engine using the final straw and the rubber balloon. When you force air into a balloon, the rubber stretches. That stretched rubber constantly attempts to snap back to its original shape, storing what is known as elastic potential energy. Slide the straw's end into the neck of the balloon. Wrap tape tightly around the connection. This seal must be airtight. Any leak will bleed off potential energy before it can be converted into motion. This schematic of the balloon's interior reveals the fluid dynamics at work. High-pressure air is trapped inside. Once released, the high-density air seeks equilibrium, forcing its way out through the narrow channel of the straw, creating a concentrated jet of thrust. Mount this engine assembly securely to the cardboard chassis using tape. The orientation of the straw dictates the car's direction. Ensure the straw points directly backward. If the exhaust jet angles sideways, you introduce lateral drift, wasting forward efficiency. You have now built a closed system. The tape, straw, and rubber are arranged to transform static, trapped energy into directed kinetic force. The physical construction is complete, but the movement of this cardboard frame is governed by mathematical principles established centuries ago. In 1687, Sir Isaac Newton published the Philosophiae Naturalis Principia Mathematica, codifying the laws of motion. Within these pages lies Newton's third law of motion. It establishes a universal rule. For every action, there is an equal and opposite reaction. In our DIY vehicle, the action occurs the moment the trapped air is rapidly expelled backward out of the narrow straw. The reaction happens simultaneously. The expelled air pushes back against the system, driving the physical chassis forward with equal force. The scale is small, and the materials are common. However, the mechanics are identical to those used to launch orbital rockets. Mass is ejected in one direction, forcing the vessel in the opposite direction. Let's initiate the launch sequence. Blow through the straw to inflate the balloon. Once it is full, immediately pinch the end of the straw tight with your finger to hold the system in stasis. The system is now pressurized. The stretched rubber is pulling inward, trying to force the air out. The potential energy of the entire vehicle currently relies on the integrity of your cape seal. Place the car on a flat surface. Release your finger. The potential energy instantly converts to forward velocity. Run the test several times. Observe the relationship between the starting volume of air inside the balloon and the total distance the car travels. Notice the deceleration phase. The car eventually slows to a stop because the kinetic friction acting on the axles and wheels eventually overcomes the diminishing thrust escaping from the deflating balloon. Now that you have a functional baseline, start changing the variables. Build a second iteration with larger wheels or a heavier cardboard chassis. Add a second balloon engine to see how increased thrust interacts with increased mass. Observing these mechanics doesn't require a laboratory. You only need curiosity, precision, and a few everyday materials to see physics in action.